Okay, check, check. Can you hear me well? Okay, good. Okay, hi everyone. So my name is Yi-Kuan Chiang. I'm a faculty member at CII in Taiwan, which is where I'm from originally. And before coming back to Taiwan, I was a former CCAP fellow for about 2 years from 2019 to 2021. And people recognize that this is especially a tough time for probably most of us during the COVID-19 pandemic. And in fact, more than half of my Oscar coffee were in this online mode of Zoom. And I'm here in this little square. And looking back, I think this is still kind of a reminder for us, even during the very tough, difficult time. We can still bring our science community together, and I'm very fortunate to have received a lot of support from colleagues and mentors at OSU. And so today, I will be talking about my recent work on the first detection of the cosmic CO and C2 background. So let's get started. So the overall science question I'm trying to answer for my career is a very broad question on how does the universe evolve. So here is a brief kind of illustrations on several key phases of the cosmic history, starting from the Big Bang initial condition, followed by early universe relic radiation of the cosmic microwave background. After that, there's no galaxies existing in the dark age of the universe. But soon after the first stars and galaxies form, the universe, the intergalactic median is reionized, and there's an extended period of time where galaxies grow and form to the rich diversity we are seeing today. And on the right-hand side, this is what I'm going to focus, one particular component of the baryonic components of the universe, the cosmic star formation history. And this is a famous plot from John, precisely 20 years ago, showing the cosmic stellar mass density growth as function of time. And from cosmic noon, about ratio 2 to 3 to present day, actually the star formation rate density of the universe is dropped dramatically by more than a factor of 10. So the big question is what drives this evolution of star forming activities in the universe? And related to the topic, the CO and C2 background, actually this star formation activity can be observed in another very bright and significant background, the cosmic infrared background, which is the dust reprocessed radiation, a thermal emission of dust powered by star formation. And connected to one of the key things of CCAP, probing the origin of structure with galaxy surveys. So I want to show this beautiful slice of the universe probing three-dimensional larger structure from DESI year 1 data. And of course, you see visually these filamentary structures, galaxy clusters and voids, and so on, the beautiful three-dimensional structure of the universe. And for a typical imaging surveys require two-step process. A galaxy rescue survey requires a two-step process. First, you do a wide field imaging survey to identify galaxies one by one. But that's only a 2D locations of galaxy catalog, so you need spectroscopy to follow up each individual object to get redshift measurements to map out the 3D distribution of structure. And what I got interested in recently, and also the topic of this talk, is an alternative way to probe the 3D distribution of the universe using a new technique of so-called intensity mapping. So intensity mapping is a slightly fuzzier way to map out the distribution of matter in the universe. And the key idea is that in addition, as opposed to counting galaxies one by one, why don't we just collect a bunch of photons and use all photons and analyze the aggregated radiation as an intensity field? And this way you bypass the requirement of source detection. And now you recognize that to resolve galaxy size, it's typically on a few kiloparsec. But a typical cosmology analysis will always have some scale cuts. And a typical scale cut might be a few megaparsec. So by not doing source detection, you win by a requirement of 1,000 times lower resolution requirement. And you can build your instrument to focus more on efficiency and volume and depth and so on. So intensity mapping is potentially kind of a efficient way to map out the universe. Of course, it's not only about efficiency. There is extra information. For example, if we collect all the lights, there's always contribution from the faint end of galaxies. There could be low surface brightness galaxies, and eventually gas outside galaxies, diffuse gas outside galaxies, even before the first generation of galaxies are formed. So one key example of two-dimensional intensity mapping is the CMB experiments mapping out early universe radiation. And of course, to map out the 3D structures at later time, one particular approach is to use strong lines, so line intensity mapping. You can pick one of your favorite lines. For example, CO rotational lines is tracing molecular gas and field of star formation, and C2 is tracing star formation rate itself. If you have some capability of doing spectral mapping, you do the wide field maps in different frequency channels. You map out the 3D structures of the universe. There is also a key challenge, a lot of foreground from the Milky Way itself and in front of the larger structure. But also there is coeval continuum, for example, the cosmic infrared background that I showed earlier. And because the lines are fainter than the continuum, you need to have some way to isolate the signatures. Despite the challenge, there is extensive experimental landscape for line intensity mapping for several key lines, for example, 21 centimeter H1 transition, CO and C2, Lyman alpha, and optical lines. And very recently, there are exciting progress on 21 centimeter H1 transition. Later last year and earlier this year, there are two collaborations, Chiang and Mir class, independently report first detection of 21 centimeter fluctuation autocorrelation. So those are big milestones after more than a decade of LIM experiments. And there's also interesting detections on diffuse Lyman alpha from a ground-based experiment, HEDEX. So CO and C2 are in the millimeter and far infrared. This basically overlap with the cosmic microwave background community, become a sub-community of CMB experiments. And these LIM experiments will require higher spectral resolution than typical CMB analysis. But here is the latest status of CO power spectrum, P of K versus wave number K. And all these data points are actually upper limits from different experiments. So there's no solid detection yet. And the solid lines show different theory predictions on the power spectrum level. What I want to draw your attention is just the range of y-axis plotted as factor 1,000 in power spectrum. So that's how uncertain these line fluxes are. So we just don't know the CO-C2 line flux yet. So it's hard to predict when are we going to make progress on CO and C2. So the big question that I ask myself is what's our best bet for first CO-C2 detection? The classic line intensity mapping is to build a spectroscopic mapping machine to map out different frequencies, and higher resolution you get, higher spectral resolution you should get, the lines are going to be dominating the fluctuations of these channel maps. But that kind of data sets are not deep and wide enough. We have a lot of pilot surveys. So what I have been thinking is to use broadband data. So we do have low resolution broadband data over entire skies, for example, from Planck, very deep, lots of photons there. What's lacking is redshift information. This kind of broadband map will become continue dominated. But if I do cross-correlation aggressively, tomographically as function of redshift, I can try to recover spectral informations by doing this synergy. So with that, I took all the wide field intensity map from the community. There's 11 map from Planck, Herschel, IRAS. Planck and IRAS are full sky, and Herschel is about 1,000 square degree. Together, these 11 map cover a factor of 50 frequency range from far infrared to millimeter. And that cover both the CIB and spectral lines that I'm interested in. And of course, visually, you see that all these maps are dominated by Milky Way foreground, so I need to clean the Milky Way and actually spend 2 years to make entirely new dust maps to be able to do this foreground cleaning robustly and try not to kill my signal of CIB in the background. And just cleaning the Milky Way by this template is not enough. I need 3D redshift information, so I cross-correlate the photons in every one of these maps with galaxies in Sloan Digital Sky Survey. It's a spectroscopic redshift all the way from redshift 0 to 4. And so the data vector is going to be very huge, so number of broadband maps cross number of redshift bands. What I get is this spectrum of the universe. So this is a tomographic cosmic infrared background spectrum, which consists of most of these continuum. This is plotted in rest frame, so rest frame emissivity as function of frequency. All these data points, every one of them is a 2-point correlation function amplitude between broadband maps and galaxies as specific redshift. And of course, there could be small line axes on top of the continuum. What you realize is that all these data points are at different rest frame frequency, right? And there is these different tracks coming from different observer band, but once we have redshift, you put this 1 plus Z factor in the rest frame. So you start to sample in very complete, very densely the spectrum of the universe. And so the broadband feature is all coming from the thermal dust emission. And you can recognize there's a characteristic peak. So that's a characteristic temperature, maybe 20 to 30 Kelvin of interstellar dust. And the overall amplitude is increasing. So color coding is redshift. So overall amplitude is increasing as a function of redshift. That's the evolution of cosmic star formation history. And on the left-hand side, I also marked the locations of CO or C2 transition. CO are a lot of rotational transitions on the low frequency. C2 is roughly right at the peak of the CIB. It's a 158 micron transition. And of course, with this giant data vector, I put out a series of 2 papers. One is about focusing on the continuum, the CIB, and then the new one is about emission line. Okay, so the highlight for the continuum is a new measurement of the cosmic star formation history. So what it is simple integration of the energy budget underneath the CIB. That's how much energy does receive from star formation, initially in the UV, but emitted in the far infrared. And just because of the sheer number of photons and the very wide field coverage, this turns out to be the most precise estimate of cosmic star formation history so far. So the red symbols and bands are the direct measurement from this cosmic infrared background. And as it turns out, this infrared component is much, much stronger than the UV, so the unabsorbed components of star formation, uncorrected for dust. And if you add the UV and the infrared together, you get to this black bands, which is the total star formation. And about 80% of that is dust obscured. Okay. And so now, again, the big question of this evolution of star formation history is what drives this dramatic evolution from cosmic noon to present day? So is it because of the change in molecular gas as a fuel of star formation, or is it a change of star formation efficiency, so converting gas into stars? So to answer this question, we really want to probe CO background because it's a tracer of the molecular gas, which connected to these tiny features of CO lines on the low frequency sites. Of course, here I marked the this is the best fit amplitude of these lines already, but one has to realize that these data points are broadband. So initially, it's a delta function of emission lines will contribute only a tiny bit of a continuum axis, a line axis on top of the continuum. But in terms of modeling, it's very simple. I just simply put delta function at the rest frame frequency of the CO and C2 lines. And C2 is by itself, it's one delta function, but CO is a series of lines. I parameterize the amplitude and also some excitation and let the data to constrain the amplitude. So here is the posterior constraint on the line strength. So this is our main result empirically. We got 3 sigma detection of C2 background. And turns out C2 turns out to be the brightest emission line in the universe in absolute energy units. And, but the SNR is not that high because it's sitting near the top of the CIB continuum, so there is a lot of more continuum noise. And CO combining 9 different transitions account for roughly only 10% of the C2 amplitude. And this is a CO luminosity density as function of redshift. This is the combined, and then different dotted lines are individual J transitions. And you recognize that the 21 centimeters sits way down there because it's a strongly forbidden transition. And for CO, with these different transitions, there's a different way to look at the excitation. So this is a posterior of the excitation as function of J, and the line ratio as function of J at different redshift. We learned that at higher and higher redshift, the CO are actually more and more excited. So they are, so I think this is the indications of a stronger or more intense star formation happening on a smaller region of galaxies. So higher star formation rate density at high Z. And if you're an instrument builder, you want to look at these posterior in the observer frame. So now this is observer frame brightness temperatures of these lines. Each line enter at redshift 0 at their rest frame frequency, but at high redshift, it's gonna shift to the left to a lower frequency. So if you're building an instrument here, for example, here 100 gigahertz, from this constraint empirical measurement, you know which CO line is dominating the line background. Okay. Key thing that we learned from the CO background is to use low J to probe molecular gas mass. So this is the omega H2 cosmic molecular gas density. And my constraints are in this block symbol. We find that there is an evolution, strong evolution, kind of mirroring the evolution of star formation history. And then the overall amplitude seems to be roughly about factor of 2 higher than previous galaxy survey measurements. Those are shown in the light blue dots. And so this is not a discrepancy yet because the galaxy surveys are not complete. Basically, they don't not complete on the faint ends, but also bright end, because even the largest kind of a single data points here only has a tiny field that is much less than 1 square degree with only a few tens of CO emitters in it. So they don't do extrapolation, and here we're using intensity mapping method to probe the total CO background. The final two things that we learned from the measurement is that if I divide the CO density by star formation rate, I'm probing the depletion time, so it's cosmic gas depletion time, which is roughly about 1 gigayears. So this 1 gigayear is, of course, shorter than the Hubble time, right? So the implication is that the molecular gas in galaxies need to be continuously replenished by cosmological inflow and cooling inside galaxies. And on the right-hand side, we actually can recover a cosmic star formation law. So this is a classic space of Kennica-Schmidt's law in plotting a star formation surface density as function of gas density. And the classic Reshef-zero relation is shown in this long dashed dotted line. And then the cosmic mean background actually kind of follow the similar trend of star formation surface density for gas surface density. So an interesting thing is that that slope is not 1, which means when you have denser gas, you actually disproportionately trigger cloud collapse in forming stars. And then this relation seems to be somewhat kind of universal. So with these different kind of line features and continuum features of the background light, we start to probe many different phases of the cosmic baryon cycles. A lot of actions occurred inside galaxies, but we're probing it on the largest integrated scale. So here's my summary. So today, what I show you is a synergy between intensity mapping and galaxy survey to report the first detection of CO and C2 background and learn physics about star formation cosmologically. And just one more advertisement. So I actually have off-cycle funding to hire postdoc in Taiwan. And so for adventurous young students in the audience, please come talk to me after the talk. And I'll stop here, and thanks. Thanks. Yeah. Uh-huh. Okay. Right, right. Yeah, yeah. So in terms of absolute line lengths, CO is about factor of 10 fainter than C2. But you see this on the left-hand side, the continuum actually differs by 2 or 3 order of magnitude between this frequency. So that's the main factor, yeah.
For the Schmidt law plot,
yeah.
I would guess that the star formation surface density comes from the temperature, the peak of the
Yes.
dust continuum, is that right?
No, it's from the CO excitation ladder.
It's from the CO excitation?
Yeah, yeah.
You get sigma H2?
Right, so that I don't know, but what I can get is the depletion time from dividing molecular gas mass with star formation density, and the depletion time determine the diagonal track. So I have the y-axis from CO excitation, I have diagonal track, so inverse engineer the gas surface density.
Okay, great, thank you. Want to do one more? If nobody else is going to ask, have you checked if the CO excitation?
Yeah.
The CO excitation sled, just the overall sled should track with flux, which should track with the temperature, should track with the RIR peak. Is there?
Let's.
I mean, it does. Obviously, it's moving, but
yeah.
Just the thermodynamics of that, I guess, work
in terms of the sign of the evolution, they're both increasing to a higher redshift, but I'm hesitant to draw a conclusion on a causal relationship. Feel like, so I think the sled is tracing more how compact the soft ISM is at high redshift. And then, so I think maybe the dust temperature is kind of a consequence of that. So it feels like they're connected, but yeah.
Temperature should encode the
Yeah.
star formation rate surface density,
Yeah.
which would also be connected.
Exactly,
So it feels
yeah.
like there's a consistency check there.
If you have a model, I'd love to see if they're consistent. Yeah.
Okay, thank our speaker again.
Okay, thank you.